Good morning, everyone. I am Professor K. Vidyasagar, working in the Department of EIE, VNR VIGNANA JYOTHI Institute of Engineering and Technology. And today, I wish to discuss the microprogrammed control unit. And most of the people will feel difficult to understand the basic phenomena of this microprogrammed control unit. Right. So we'll start this microprogrammed control unit today. Right. Look at, I organize these instructions into two types. One is the machine instruction, another one is the micro instruction. It is representing three phases of the machine instruction: fetch the instruction from the memory, decode the fetched instruction, and execute the instruction. Right? These machine instructions are stored in the main memory, that is your RAM locations, and microprogram instructions are stored in ROM locations. That memory is called the control memory. Right? A set of machine instructions arranged in an order is called a program that everyone knows. Now the machine program composing of machine instructions, those machine instructions are stored in the RAM locations as I stated earlier. And micro instructions are stored in the ROM locations. Now each micro instruction consisting of micro operations. There are certain field bits in the micro instruction, field 1, field 2, field 3 bits. All these three fields will produce three micro operations. So I will come back to this slide again. Look at this one. Now I am trying to execute the machine instruction. During the clock pulse T0, when clock makes a positive transition, the contents of PC is transferred to the address register. This is happened during the clock pulse T0 when clock makes a positive transition. And subsequently, in the next clock pulse T1, when clock makes a positive transition, two micro operations are performing. One is increment the contents of PC by 1, and then access the memory with the AR register. The address of the AR register is already loaded by the PC. Now access the memory location and get the information, that is the instruction, which is stored into the instruction register. And during the clock pulse T1, when clock makes a positive transition, two operations takes place simultaneously. Now one is increment the PC pointing to the next memory location in a sequence, and another thing is memory read the memory. Read the memory. M of AR. AR register is the address register used to access the memory to fetch the instruction from the memory. The fetched instruction is stored into the instruction register. Now I am moving to the next thing. Look at this. This is the machine instruction cycle. I already stated that instruction cycle is composing of fetch the instruction from the memory. Already these three micro operations determine the fetch cycle, fetch the instruction from the memory. And the next one is decode the fetched instruction from the memory. Right? See, look at this one. So there is fetch the instruction from the memory. These three micro operations will determine fetch the instruction from the memory. Now decode the instruction from the memory. So the machine instruction is, the length of the machine instruction is 0 to 15 bits. That means 16-bit instruction. 0 to 11 bits determines the address field. 12, 13, 14, 15 bits are called operational bits. And this 15th bit, IR15, I call it is IR15, representing the mode of the instruction it is. Right? So based on that, we have to decode the instructions. Look at this. IR 0 to 11 address bits which are stored into the instruction register. That is IR 0 to 11 bits transferred to the address register. So that means if it is an address, then I have to access the memory to get the data for execution of the instruction. That is the reason why address bits IR 0 to 11 are loaded into the AR register. In the next subsequent M of AR, is, that means memory is accessed with the address register. The address register, the address of the memory location is represented by IR 0 to 11 bits. So M of AR access the memory, get the data, load into the DR register. So data is loaded into the, that is the reason why we are loading IR 0 to 11 into the address register, right? Now IR 12 to 14 bits, these are determining bits, what type of instruction it is. Is that instruction is a memory reference instruction? Is that instruction is a register reference instruction? Is that instruction is an IO reference type of instruction? So if you classify the instructions based on the kind of memory accessing it is. So memory reference direct. So if I considered a memory reference instruction, is that address is a direct address or an indirect address, that will be determined by IR 15. That is the reason why IR 15 bit is transferred to the I flag, right? So if that bit is, if 12, 13, 14 bits are 0002 110, that means 12, 13, 14 bits lies within 0 to 6. Lies within 0 to 6 and IR 15 is equal to 0, that indicates the instruction is a memory reference direct instruction. Now the address of the memory location is a direct address. That address is represented by the IR 0 to IR 11, which are loaded into the ER register. You got my point? If suppose IR 12, 13, 14 bits are lies within 0 to 6, but IR 15 is equal to 1. If I convert into a hexadecimal code 1000, that comes under 8. 1000, that is 8. So you are skipping between 0 to 6. If the IR 12, 14, 13, 14 bits lies within 0 to 6, IR 15 is equal to 0, memory reference direct. If IR 12, 13, 14 bits are 000, lies within 8 to E, because IR 15 is equal to 1. 12, 13, 14 bits varies between 0000 to 111. That means 8 to E. 8 to E. Now that instruction is a memory reference indirect instruction, because my IR bit is equal to, IR 15 bit is equal to 1. 12, 13, 14 bits varies between 0 to 6. So that instruction is a memory reference indirect instruction. That's what we are decoding the instruction. IR 12, 13, 14 bits are all not lies between 0 to 6. Those bits are all ones. 12, 13, 14 bits are all ones. That means equivalent in decimal, that is equal to binary equivalent is equal to 7. So IR 12, 13, 14 bits is equal to all ones. So the instruction is not a memory reference instruction. Now I am verifying whether it is a register reference or IO reference. So IR 15 is equal to 0. IR 12, 13, 14 bits are all ones. Now it is a register reference instruction. In that case, IR 0 to IR 11, those bits representing the kind of instruction it is. You know, clear the accumulator, complement the accumulator, clear the flag, complement the flag, circulate right, circulate left, right? So those are all register reference instructions. In similar fashion, if IR 12, 13, 14 bits are all ones, IR 15 is equal to 1. It is not a register reference instruction. It is IO reference instruction, right? So in that case, IR 0 to 11 bits representing what type of IO reference instruction. If I said F800, read the date, IN instruction, F840, F400, write out the instruction. Clear. See, these are all IO reference type of instructions. Look at this during the clock pulse T2. When clock makes a positive transition, remember the register transfer is sensitive to the rising edge of the clock pulse. So it is not sensitive to the falling edge. It is a rising edge, leading edge or rising edge of the clock pulse. When clock makes a positive transition, it transit from 0 to 1. 3 micro operations are performing. One is the transfer micro operation. IR 0 to 11 bits are transferred to the AR register. IR 12, 13, 14 bits are transferred to the decode logic circuitry. IR 15 is transferred to the I flag. 3 micro operations are performing during the interval T2, during the clock pulse T2. We can call it as interval of the clock pulse T2. So I can say it is the leading edge of the clock. Please remember, my friends, leading edge of the clock pulse. When clock makes a transit from 0 to 1, 0 to 1, during that time, these 3 micro operations takes place. All these micro operations are grouped as a decode phase of the instruction. When I consider during the clock pulse T0 and T1, 3 micro operation takes place. During the clock pulse T0, when clock makes a positive transition, the contents of PC are transferred to the AR register. During the clock pulse T1, when clock makes a positive transition, increment the contents of PC by 1 and then access the memory, fetch the instruction, load into the IR register. Those are formed as a routine. These 3 micro operations related to the fetch instruction formed as a routine, we call it as a fetch routine. And similarly, the decode instruction, IR 0 to 11, that is the address bits transferred to the AR register. 12, 13, 14 bits transferred decode logic circuitry. IR 15 mode bit, we can say it is a mode bit. It is transferred to the I flag. These 3 micro operations are confined to the decode operation. So we can simply call it as a decode phase of the instruction or decode routine of the instruction and decode cycle of the instruction, and subsequently we can call it as a fetch cycle, because this is repeating for every machine instruction execution. These 2 cycles are mandatory, right? So I am moving towards how this instruction will be executed. Remember, I already stated the instructions classified memory reference instructions direct, memory reference instructions indirect, register reference instructions, as well as IO reference instructions. So the instructions types are varying. Some of them will be called as, the instructions may be classified as transfer type of instructions, logical instructions, arithmetic instructions. These 2 called as a data manipulation instructions. And program control instructions classified program control conditional, program control unconditional. Jump to the specified location. Jump if the condition is satisfied. Jump to the specified location. These are conditional based instructions. And some instructions will be called as program process control instructions. Halt the processor. Stop the execution of the processor. And some of them will use no operation to introduce some delay. That is, you wanted to force the processor into the idle state, doing nothing, and during that time. So because my device, which is connected to the processor is accessing the data from the device speed is very slow, process speed is very fast, because it is operating with 3.2 gigahertz clock frequency, and that device is operating in megahertz clock frequency. Asynchronously, these 2 devices are operating. So the processor may require a wait cycle to access the data from the device. You understood? So that is the reason why you may pause the processor execution. You may force the processor into the idle state condition by introducing the no operation. Inherently, I am doing wait. I am providing a significant delay. That is a no operation. See, similarly, there are certain different types of instructions. Processor control instructions, program control instruction, conditionally, unconditionally. Data manipulation instruction, organized as a register reference instructions, as well as logical instructions, and or not, exclusive or operations, logical instructions. Understood? Add, subtract, add immediate, subtract, multiplication, division, increment. Those are all arithmetic instructions. Data manipulation instructions. Data transfer instructions are called move the data, from register to the register, move the data from memory to the register. See, all these registers are different kinds of execution performance. Sorry. So that is the reason why I cannot consider same set of micro operations for executing your machine instruction. Right? So remember this point. We have to recall this concept while discussing the routines of the micro program. I will address it later. Look at this. Already we completed fetch phase, we completed the decode phase, and we are moving towards the execution phase of the instruction. Execution phase of the instruction. Look at this. The instruction is going for execution, and see, this is an add operation. The contents of the accumulator performs an add operation with the contents of the data register, right? And the result of the operation is transferred to the accumulator. This is happened during the clock pulse T3 when clock makes a positive transition. Remember that, because this operation is an addition operation. The sum of the contents of the accumulator with the contents of the data register, the result is transferred to the accumulator. I will explain one point at this stage, why the result is transferred to the accumulator. Here you can find one conflict at this stage. What is that conflict? Data register is having the data, because during the decode phase, IR0 to IR11 transferred to the address register. That means you are accessing the memory location to get the data. This is the memory read operation. Read the data from the memory, the address of which is loaded by the AR register, that is the address register, and the extracted data is transferred to the data register. One data you loaded into the data register. What about the accumulator? That is a default register, which is because your processor is an accumulator organizer processor. If the processor is an accumulator organizer processor, all the arithmetic operations, logical operations must be performed its operations with accumulator only. And second concept, the result of which is transferred to the accumulator only. Because my processor is an accumulator organizer processor. My processor is not a register organizer processor. If suppose the processor is a register organizer processor, then I have to represent the register 1 plus register 2, and then the destination register also I need to specify, because my instruction is a 3 address field instruction. If my processor is a stack related processor, I have to use push the instruction into the stack location, push the second data into the stack location, perform an add operation. This is a 0 address field instruction, add. If I wanted to perform a subtract operation, SUB, that is a 0 address field instruction, because my processor is a stack related processor. Because in our context, our processor is an accumulator organized processor. We have to obey the fundamental principle. It is the processor register that is an accumulator. Why it is called a processor register? All the arithmetic operations, logical operations must be performed with accumulator only. So my second operand is provided by the accumulator. Second concept, after performing the addition operation, the result is to be transferred to the accumulator. And one more thing is, if you wanted to access peripheral devices are interfaced with the processor. Read the data from, that is F800, that is IN operation, IN, AL, comma, address of the input device. Read the data from the input device. The address is represented within the instruction. IN, AL, comma, 80H. 80H is the address of the input device. Read the data from the input device and then load into the accumulator, because accumulator is acting as an intermediate register between the processor and the input device. Similarly, F400, that is the code of out instruction. Out the data, out, specify the destination address, out, 82H, comma, accumulator. That means transfer the data from accumulator to the output device. The address of the output device is represented within the instruction. You got my point? Out 82H comma accumulator. Sourcing the data is accumulator. Destination device is my output device. The address is represented within the instruction. This is IO direct addressing mode of instruction. Mode of addressing is direct. Address of the peripheral device is represented within the instruction. Those are IO reference instructions. To access the output device, to access the input device, accumulator is acting as an intermediate device between the input device and the processor and the output device. So processor will not directly read the data from the devices. Devices will place the data onto the data bus. Processor will read the data from the data bus and load into the accumulator. That is the reason why the third source to call the accumulator is a processor register is accumulator is an intermediate source between the input and output devices. So that is the reason why this accumulator is called the processor register. So this is the instruction we are having. So I am elaborating the things in detail. Why accumulator is acting as a destination register, why accumulator is providing the second data to perform the addition operation. See, when you look at this one, execute the instruction. For this add operation, I used accumulator plus DR. If I consider a jump operation, instead of this add operation, I can say JC, some address associated with some address. What does it indicate? The address is represented, the operation is represented. You cannot say both the instructions are having same execution phase. Both the instructions are having same different, independent, unique execution phase. So you cannot consider it is a common routine for executing all machine instructions. You got my point? You remember this point because we have to discuss why routines will be used in the microprogrammed control unit. Right? That's all with this machine instruction cycle. I'm moving forward to the next cycle. Next slide. Look at this. So this animation I created, but I would like to see 3 blocks I provided there. One is the RAM. We call it as a main memory. I used to call it as a physical memory, and I can call it as a primary memory. Right? Now, why it is RAM is called the main memory? Whatever may be the data, processor will access. The data is in the RAM memory. Your processor directly access the RAM location. It will not access the secondary memories. If the data is not available in the RAM memory, then processor will send a request to the operating system. Please provide the data. The required page of information is not available in the RAM location. Please provide the required page of information. This is the demand will be sent to the operating system. Then the operating system will scan the entire secondary memories, that is your hard disk. Identify the required page from the secondary memory and then brought into the RAM locations. This is called page translation. So I can extend this. If the RAM is full of information, there is no room to accommodate your page which is brought from the secondary memory, then operating system will identify a victim page from the RAM location. That is called, you execute, operating system itself will execute either the FIFO, first in first out replacement algorithm, or random replacement algorithm, or least recently used algorithm, or optimum replacement algorithm. Any of these replacement algorithms will be executed by the operating system to provide a room to accommodate a new page which is brought from the secondary memory into the RAM locations. Once the page is brought into the RAM locations, the one page we identified it is a victim page which is to be flushed out from the RAM locations. If suppose any bit of that page that information is already modified previously, that page which should not be flushed out from the RAM location, it should be copied, brought back into the secondary auxiliary memory location, that is your hard disk. So a new page is brought in, a victim page is brought out back to the swap list. This is called swap out and swap in mechanism. Once this is done, operating system will inform to the processor, yes, a new page is brought. The demand page fault mechanism is completed. Then your processor will access the RAM locations. Got my point? This is the reason why I call it is a physical memory, and this is the primary memory. This is the main memory to execute any task which is assigned by the user. Got my point? So that is the main significance of the random access memory and read and write memory. Random access memory means the RAM is not sequential memory. You can access any memory location in the entire stretch of RAM locations. If I say my RAM size is 1 megabyte within 00000H2 FF, any of these memory locations within this range, processor can access. That is the reason why I call it is a random access memory. And you can say, you all very well said, it is read and write memory. Processor can read the data from the RAM location. It can write the data into the RAM location by executing your operations, right? So there is another block is there. Group of control words. A control word is stored in a memory. That memory is called ROM, read-only memory. Read-only memory. A read-only memory is called the ROM, which is stored with the group of control words. Which is stored with the control words. A control word is composing of a stream of ones and zeros, control variables. Each bit is representing one variable. This group of control variables is called as a control word that is stored in the ROM locations. The reason is the relationship between this RAM and ROM is RAM is used to accommodate the machine instructions. ROM is used to accommodate micro instructions required to execute the machine instruction. Got my point? That is the meaning of that is the relationship between the RAM and ROM locations. I'm moving what I plotted sequence. So this is a machine program composing of machine instructions which are stored into the RAM locations. Right? Machine instruction is extracted from the RAM location. To execute that machine instruction, I required micro instructions. You already you have seen micro operations. I will explain it. Right? Micro program. A group of micro instructions is called a microprogram. A group of micro instructions is called a microprogram. Each micro instruction representing in the form of a control word. Right? Look at this. Microprogram is stored in the ROM location. Machine program is stored in the RAM location. Right? To execute the machine instruction, I required a micro instruction. Where this micro instruction is, that is in the ROM. In which routine, that I don't know. We have to find out where the micro instruction is available. That is called address of the ROM location to fetch the micro instruction for execution of machine instruction. Got my point? Look at this. Right? Microprograms are stored in the ROM location. If I access the ROM location, I can get the micro instruction. If I decode the micro instruction, I can get micro operations. Those micro operations are required to execute your machine instruction. Got my point? Look at this. Your micro instruction releases micro operations. Remember, these micro operations, I pose one question. A micro instruction will release maximum of how many micro operations? I will tell you. A micro instruction composing of 0 to 7 bits, address bits, 8 to 9 branch bits, 10, 11 conditional bits, 12, 13, 14 bits are called field 1 bits, 15, 16, 17 field 2 bits, 18, 19, 20 field 3 bits. You got my point? So my length of micro instruction is 21 bit. Within this 21 bits, we organized this micro instruction into the address bits, branch bits, conditional bits, and field 1, field 2, field 3 bits. Each field composing of 3 bits. So I can provide 1 micro operation out of 8 from field 1. Subsequently, 1 micro operation out of 8 micro operations. 1 micro operation from field 3, 1 micro operation from field 2, 1 micro operation from field 1. Maximum of 3 micro operations can be generated by using 1 micro instruction. You understood? I'll see. These micro operations are required, essential, imperative for execution of the machine instruction. Got my point? Look at this. Micro instructions are stored in the form of a control word where you are storing into the ROM location. Got my point? Micro instructions are stored in the form of a control word. This control word is stored into the ROM locations. If you access the ROM location, you will get a micro instruction. The micro instruction will generate micro operations. Those micro operations are required for execution of the machine instruction. Identify the sequence. Look at this. A group of control words is called a microprogram. Excellent. A group of set of control words, that means set of micro instructions, is called a microprogram. You can say set of micro instructions arranged in a sequence. Look at this. This is the micro instruction format. I already explained 0 to 6 bits are address bits, 7, 8 bits are called the branch bits, 9, 10 conditional bits, 11, 12, 13 field 1, field 3 bits, 14, 15, 16 field 2 bits, and 17, 18 field 1. So I might be wrongly specified. Field 1, field 2, field 3. Alright. Look at this. Condition bits are called unconditionally. It is always 1. If my CD bits, 9, 10 bits are 0, 0, unconditionally. If my most significant bit of my instruction register, IR15, that is equal to 1, that is called mode bit. Similarly, my data bit, my data which is extracted from the memory is stored into the DR register. The most significant bit is equal to 1. IR15 is equal to, that is indirect bit. IR15 is equal to 1. Indirect. Accumulator is equal to positive. Accumulator is the most significant bit of the result of the operation representing sign of that number. If my sign is positive, then condition bits are 1, 0. My condition is true. And similarly, if the result of the operation is 0, accumulator is equal to 0, my condition bits representing 1, 1. If any of these conditions satisfied, if any of these conditions are true, then there is a meaning to the branch bits. Otherwise, you can neglect the branch bits based on the condition is unconditionally, jump to the address bits. If provided my test condition, the condition bits are failed. That means the condition is not true. So, jump to the next address in a sequence. That's what. So, similarly, look at this one. There are branch bits are represented, jump. If branch bits are 0, 0, jump to the specified address. Jump to the specified address. In the functional operation, you can visualize the AD bits are transferred to the CR register. Control address register is used to access the control memory that everyone knows. Right? Now, if branch bits are 0, 1, call the subprogram. This is used to access the subprogram. Call the subprogram. Remember, whenever you are branching to some other location, you have to save the return address. That is the next address which is to be accessed. The return address is to be saved before you execute a subprogram. Before you branch to execute the subprogram, you have to save the return address. Where you will save the return address, that means the next address is PC plus 1. I already stated increment the contents of PC by 1. Increment the contents of PC by 1. That means the next address which is to be executed, but instead of executing the next address location, you are branching to execute a subprogram because your branch bits are 0, 1. Call and read, these two are used for subroutine instructions. Call the subprogram. You are branching to the address location of the subprogram. Your address of the subprogram is loaded into the CR register. Next address is incrementing by CR by 1. That is the next address, return address, which is stored into the subroutine register. Remember, as you studied, the condition here is, if you wanted to load a data into a register, you must enable the load variable of that register. Got my point? Load the data into the load control variable is equal to 1. If my control variable load is equal to 1, then only I can load return address into the subroutine register. Remember this point, it is very important. And next one is return from the subprogram. After executing the subprogram, you can return from the subprogram. For that, your branch bits are 1, 0. Any of those conditions are true. Branch bits are 1, 0. So, return from the subprogram. Understood? So, I am accessing the subroutine register, and subroutine register will provide the return address and load into the CR register, access the control memory. You can resume back to the original program where we left off. Return to the original program. And last one is external mapping. When you reset the processor, the initial address of is to be mapped into the CR register, control address register. This is an external mapping. How you do the external mapping? Transforming the opcode bits of the machine instruction into the address bits of micro instruction. What are the address bits? 0 to 7 bits. So while mapping these address bits, the control address register address bits 0, 1 and 6. These bits are initialized with 0, and 2, 3, 4, 5 bits are mapped exactly with the opcode bits of the instruction. You can see here, you can see it. See, look at this one. This is these CR0, CR1 and CR6. These bits are initialized with zeros, and 2, 3, 4, 5 bits are mapped with the opcode bits of the machine instruction. This is called mapping logic. Mapping logic. This is what you can call mapping of the opcode bits of the machine instruction into the address bits of the micro instruction. This is called mapping operation. This is happened only when if my conditions are true, any of the conditions are satisfied, or unconditionally, if my condition bits are 0, 0, unconditionally map because my branch bits are loaded with 1, 1. Got my point? And subsequently, there are certain field bits, 3 bits representing 8 micro operations. These 3 bits representing another 8 micro operations. These 3 bits representing another micro operations. Right? Look at this. Each 0, 0, 0. It is no operation for all cases. And this is 0, 0, 1. Add operation. For all these operations, there are 5 letters we considered for transfer operations. Look at this. These are all accumulator, clear the accumulator, CLR accumulator, increment accumulator, data register to T. There is a T between 2 registers, data register to accumulator, right? See, data, you have to speak like this. Data register to accumulator, data register to address register, PC to AR register, write operation. These are the micro operations provided by field 1 bits. Generally, this is field 1, field 2, field 3, wrongly represented. So, you please correct it. So, these 8 operations will be provided by these 2 field bits. These 8 operations will be provided by these 3 bits, right? So, you can decode the micro operation like this. I'm moving forward to the next slide. See, look at this one. If the condition is true, then there is a meaning to the branch bits. That is my intention. If the condition is true, then there is a meaning to the branch bits. Otherwise, if the condition is not true, The next address is represented within the instruction. The address bit 0 to 6 representing the next address. Right? So this is the binary representation of the micro instruction format already represent. Look at this, you can interpret it. The address bits are initially 0, 0, 0. Now branch bits are 1, 1. As you stated, it is a mapping logic. Condition bits are 0, 0. Unconditionally map. Right? Unconditionally map means mapping of the opcode bits of the machine instruction into the address bits of the micro instruction. Right? So such a way that you can decode this one. So there is a fetch operation. See, this is origin 64. This is a routine address 64. Origin 64, that means origin 0 to 60, routine 0 to routine 63. That means 64 routines are there because my control memory is decomposed into routines, 64 routines. Each routine composing of 8. 64 into 8. How much it will be? 512. Right? So my control memory address is 512. That means 2 power 9. It is a control bits. If suppose my control memory is 128 bytes, 2 power 7 address fields. Now to 128 bits. Right? So such a way that you can see PC to AR, fetch the routine. Already we discussed this one. Read the data and increment PC. These two takes place within 1 clock pulse, and address register is transferred data trace. This is the mapping operation. Right? This is very important. The next address generation. I access the control memory. One micro instruction is extracted. What is the next micro instruction? What is the address of the next micro instruction? Who will represent this? So this block, the next address generation sequencer will determine what is the next address of the instruction. So that is loaded into the control address register. See, look at this one. We have a control memory. Now I will represent the control memory. This control memory is to be accessed with the control address register, CR register. Right? If I access the control memory with this CR register, I can get some micro instruction that is in the form of control word. That control word is stored into the control data register. One instruction is accessed. Control address register is accessing the control memory. Now one micro instruction is loaded into the control data register. What about the next micro instruction? That is determined by next address generation circuit. This will determine what is the next address of the control memory. So once this is determined, the next address, now control address register is loaded with the next address, and then access the control memory and fetch the one micro instruction. The micro instructions are stored in the control word format. That micro instruction is stored into the control data register. Right? So now this is the continuous process. Now look at this one. We will elaborate this next address generation circuitry in our next slide. Look at this. I provided some significant blocks. I considered a multiplexer there because I have 4 possible sources to feed the next address into the control address register. That is the reason why I considered 4:1 multiplexer. At a particular instance of time, only one micro instruction can be accessed from the control memory. One micro instruction address can be loaded into the CR register. Right? So this multiplexer is having 2 selection lines, S0 and S1. Right? So this is a subroutine register required to load the written address. This is an increment logic which will increment the CR by 1. This is my conditional operations to be unconditionally indirect address, and this is memory. This is an indirect bit, and this is a sign bit. This is the 0 state of my execution operation. UASZ. These four conditions, any of these four conditions must be satisfied. So a test logic is generated. If the test logic output is equal to true, then there is a meaning to the branch bits. The branch bits are loaded into the input 0 and input 1 of the input logic. I call it is a branch logic. This is a branch logic, right? Now I am moving forward. This is a micro instruction. 0 to 6 bits are address bits, 7, 8 bits are branch bits, 9, 10 are conditional bits, 11 to 19, these 9 bits are field bits. Okay, I'm moving. Right. So what is this? Control memory. What information stored into the control memory? Microprogram. What is microprogram? Consisting of micro instructions. This is the current micro instruction. This is the current micro instruction I represented. Organized into the address fields of the control memory. Anyone can respond. 0 to 6 bits. 7 bits assigned as an address bits. That means 2 power 7 addressable memory locations of this control memory. The power 2 power 7, the power 7 is used to represent the size of address of the control memory. You got my point? That is represent 2 power 7 addressable memory locations. 128 bits. 128 memory locations. My control memory is just 128 bytes. If suppose I assign here 8 bits, that means address bits are 8 bits means 2 power 8, 256 bytes. If my address bits are 12 bits, that means 2 power 2 into 2 power 10, 4 kilobytes. My control memory is 4 kilobytes. So I can represent address bits. So these address bits vary because my control memory, depending upon the size of the control memory, these address bits will vary. So my length of the instruction is also vary. This is the basic description of the control memory. So I considered 0 to 6 bits. Understood? Right? So now I have to access this control memory. If I don't know the address of the control memory, I cannot access. So I should know the address of the control memory location. I cannot access, but load that address into the control address register and then control address register access the control memory. Look at this. I am providing. This is the address field. This is the branch field, condition bits and operational bits. Now my control address register came into the picture. Control address register. This is the register. What is the register used to access the main memory? Address register. That is the main memory. This is the control memory. The address register. You assign a prefix C, control address register, which is used to access the control memory locations. That control address register is loaded with address of the control memory location. Got my point? Now I am accessing control memory using the control address register. See, your control address register is accessing the control memory. What happens? One micro instruction is extracted, fetched from the control memory. Look at this. That is unconditionally jump next. Unconditionally jump next. That is the symbolic representation of the micro instruction format. Symbolic representation of the micro instruction. Unconditionally jump next. What does it mean? My next address of the control memory is represented within the current micro instruction format. I will repeat. The next address of the control memory to be accessed is represented within the current micro instruction format. This is my current micro instruction format. The address is representing the next address. If I wanted to access the control memory, this is the previous address already loaded into the CR register. If I wanted to access the next address, increment the CR by 1. You can go to the next address. Look at this. I am incrementing the CR by 1 and next address is sequencing. You got my point? See, your next address is loaded into the CR register. This is the next address. Now again the control address register is accessing the memory. Control memory is accessed. So This is if the sign bit is positive, then jump to this address. What is this address? If the sign bit is positive, then jump to this address. In some of them will say, if the sign bit is negative, then jump to this address. The condition here is whether the sign bit is conditional bit is satisfied or not. Is condition bit is true or not. If the sign of the number is positive, then jump to this address. If the sign of the number is negative, then jump to this address. See here, the condition bits are 0, 0. The branch bits are 0, 1. This is the address of the branch location. Now the condition is true, then branch to this address. This is the branching address. Load into the CR register to access the control memory. You got my point? So you will check it out, how it is happening. Right? This is the address. Next address is to be transferred. This is the branch address. When this branch address takes place, see, your CR register, branching, condition is true, then jump to the branch location. This address is loaded as the next address into the CR register. Two possible sources we discussed. One is increment the CR by 1, sequencing the next micro instruction, sequencing. This is increment the CR register by 1 because unconditionally jump next. Other one is, if my condition is true, if my sign bit is true, jump to this. This is called the branching address, not the next address. Because this is a jump is called, jump is branching, jump to this, a branch to some other location, if provided your condition is true. If I say the condition bits are 0, 0, these bits are 0, 1, unconditionally jump to this address. Got my point? If my condition bits are 0, 0, branch bits are 0, 1, and this is the address. So unconditionally jump to this address. But in our case, the next instruction we fetched, that is, if the sign bit is true, that is, if the sign is positive, then jump to this address. I will move next one. Look at this. Now the condition bits, jump bits are loaded into the test logic. Verify the test logic. Is the condition, if the sign is positive or negative? Check it out. Look at this. Right. Now branch bits is 0, 1, that is transferred to the input logic, input 0 and input 1. Now the test condition CD bits are transferred to the test logic. What are the CD bits? 0, 1. Branch bits are 0, 1. Now here the testing operation takes place. Yes, the condition is true. Verify it. If the condition is true, then load the branch address. You see, this is unconditionally call. Unconditionally call. Call is the instruction which is used to access the subprogram. Now, the condition bits are 0, 0. Unconditionally call the subprogram. What is the subprogram address? Represented within the instruction. Right? So, I am moving forward. Unconditionally call the subprogram. Right? Look at this one. Unconditionally call the subprogram. What is my next address? Subprogram address. That is represented in the current micro instruction format. You got my point, right? I will check it out. Is this workout? Unconditionally call the subprogram address. The condition bits are transferred to the test logic. Now the test logic branch bits are transferred to the branch logic. That is your input logic. Verify the test logic. Is the test logic is failed or condition is true? If the condition is true, there is a bit T bit that is equal to 1. If that is equal to 1, the return address is loaded into the subroutine register. So the load control variable is released by the input logic. If the load control variable is released, now the incremented value, that is the next address in a sequence, is loaded into the subroutine register. Right? See, this is then the return address. Return address. We are loading into the subroutine register. You got my point? We are loading into the subroutine register. Yes, look at this. I will go back again. Look at this. I am go back again. See, unconditionally call. Unconditionally call. Transfer the unconditionally call the branch address. Transfer the condition bits to the test logic. Verify the test logic. If the test logic is true, that means the output is equal to 1. That is the test logic. T is equal to 1. Then input logic is enabled. That test logic is verified. The condition is true. Now T is equal to 1. Otherwise, T is equal to 0. There is no meaning to the input logic. Since the condition is verified, the input logic given control signal, a load input is given to the subroutine register. Now the return address is loaded into the subroutine register. The return address is the next address, that is the incrementing of CR plus 1. Increment the CR plus 1. This is the return address is load. Now the subroutine address is transferred to the subroutine register. This is my branching address. The branch address is loaded into the CR register. Now the control is transferred to the branch location where my subprogram is to be executed. Understood? That is the significance of the branch address field. Now again we will check it out other use case. Now the branch address is accessed. The next micro instruction is accessed. The next micro instruction is the sign bit jump to this address. That is over. Already we discussed. The next instruction is unconditionally return. Unconditionally return. So return address where you saved into the subroutine register. If you decode this, condition bits are 0, 0. Unconditionally, your branch bits are 1, 0. That means the return operation, return. It is not IRET. IRET means interrupt return. This is the return. RET is the last instruction of the subprogram. Return from the subprogram. This is unconditional return. Right? The address is direct address, not an indirect address. Unconditionally return. This is the last instruction of your subprogram. Where your subprogram is executed, the last instruction is representing unconditional return. Now you decode it. Unconditionally, those bits are, condition bits are 0, 0, transferred to test logic. Branch bits are 1, 0, that is transferred to the input logic. What we have to do? Verify the test logic. Yes, condition is true. Yes, T is equal to 1. So what we have to do? The next address is provided by the subroutine register because you have saved the return address into the subroutine register. So return from the subprogram. Load the next address from the subroutine register. That's what I am doing now. Yes. If my S0, S1 is equal to 1, 0, multiplexer is loaded with the subroutine register value. Now the multiplexer will provide the output that is loaded into the control address register. That is the third possible source of finding the next address in a sequence. Return address is loaded into the CR register. Now again the control address register is accessing the control memory. I will get one more instruction. The instruction is unconditionally map. Mapping operation. This is always an external mapping. It is happened when you reset the processor. When you are reinitializing the processor, now the starting address of my control memory, that means where the boot up program is stored. So mapping is to be done there. During that process, mapping already we discussed, transforming the opcode bits of the machine instruction into the address bits of the micro instruction. That is the mapping operation should be done. So unconditionally map. That means my condition bits are 0, 0, branch bits are 1, 1. So I have to test it. Is the condition is true or not? Yes, the condition is true. Branch bits are given to the input logic. Condition is true. Now what happened? My fourth possible source to load the next address into the control address register is an external mapping. Now S0, S1 is equal to 1, 1. So fourth input of the multiplexer is selected. That is an external mapping. Mapping done. Multiplexer is loaded with the next address into the CR register. Now CR register will access obviously the control address register. These are the 4 possible ways to load the next address into the CR register. The first one is the next address in a sequence. So increment the CR by 1. Second possible source, the next address may be a branch address. So the branch address is loaded into the CR register. Third possible source, written from the subprogram. Written from the subprogram. So the loaded written address is from the subroutine register is transferred into the CR register. CR register is loaded with the written address. Again access the control memory to fetch the next instruction. Subsequently, there is another possible source of input to the CR register, that is external mapping. These are the 4 possible sources to load the next address into the CR register. Right? So, thank you very much. So, we'll continue our session in the next time. We'll continue our session. Right? Thank you. Thank you very much.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.